So just a quick recap. So Monday we discussed about the basics of the Ito integration. What are the assumptions required or restrictions required on the class of functions that we are going to use for the integration theory. So let me just scroll back. So we had this definition for the class of functions V, which I am trying to locate. Yes. So V is this class of functions, square integrability, FT adaptedness. And our integral theory started out with the elementary functions or step functions. The first result we established was the Ito isometry. Ito isometry is essentially a conversion from an expectation of dV integral to a dt integral that takes care of the variance. And then using elementary definition, we have shown one example of an integration, a simple integral, but that highlights two things. One is that the choice of the endpoint is critical. Whether I take the left endpoint as in Ito, or if I take some other the choice of T star as in Stratonovich, the results will differ. And secondly, the difference in the result from the usual Riemann integral is essentially due to the variance of the random variable under consideration. So when we are evaluating an integral, we are not only finding the resulting process, we are also adjusting for the variance of that process. So that's, I'm sorry, did I go offline? Hello?
Yes, sir.
Yeah, so
Sir, your voice is also breaking sometimes.
my voice is also,
Your network is.
my network is not so good today. Yeah, that I have understood. So all right, so if required, just give me a call. Many of you have my phone number. If there is a problem, give me a call. I will switch to some other connection. All right. So for the time being, let me try and continue with this line. And if there is an issue, just give me a call. I will switch. All right. So we were talking about the basic definitions that we discussed last time on Monday. So that the Ito integral, how it is evaluated from elementary operations that we have seen the Ito isometry, and then discussed some properties of the Ito integral, which are somewhat similar to the Riemann integral. But of course, there are additional properties because now we are handling stochastic processes, random objects. So in particular, these first two properties here are similar to the Riemann integral properties, linearity, additivity, etc. But the third and fourth one are specific to the stochastic integration scenario, where we are evaluating the expectation of the integrals, which we show that to be 0, and show that the integrals are also FT adapted. FT adaptedness would be very useful for us for financial applications. Okay, and then further on, we showed that the integrals are also martingales. The proof is quite easy. And we have shown that the integrals can be assumed to be path continuous. Because of the Kolmogorov continuity theorem, we can choose a version of the integral which has continuity property. And finally, we ended up with, a very broad outline of an extension of the Ito integral to multi-dimension. As I said, we are not going to be using it a lot, but in some financial market situations, we need to understand how asset prices behave when there are more than one sources of uncertainty. So if I have multiple sources of uncertainty, I will need multiple Brownian motions to model that. And hence, we needed an extension of the Ito integral to multi-dimension. And formally, that can be done using our typical vector matrix type of notation, as we have discussed yesterday. Monday. So that's where we stopped. Are there any questions or clarifications on those things so far? Because this is the basic theory, and then we will go on to the construction of the Ito results, the basic Ito results on which our Black-Scholes pricing model will be based. So are these basic theory points clear to all of you? And also very importantly, have you looked at the textbook? Because I am following Oxendall and sometimes I am following Whale-Portstone, and the chapter section numbers are all mentioned in the syllabus. So how do I interpret the silence? You have not yet started reading the book. Well, that, as I said, is not good, because I'm not going to discuss all the points. I'm just basically giving you an outline, a path through the syllabus. So unless you are looking at the textbook, there will be missing links, and later on they will create trouble. So, all right. So anyway, let me continue. So today, first I want to discuss a few integral properties. So these are more mechanical properties of the dt integral, because as we have already seen that there are ways of converting the dv integrals into dt integrals through some manipulations. So we need to understand the basic properties of the dt integrals. And for that, I will go to Whale-Portstone. Whale-Portstone, there is a section on this. And these properties we will understand. We will also try to see why they are useful for us in terms of our financial application. So I call them some useful results for dt type of integrals. Some of them are straightforward, like the first one. If I take a function ft and a stochastic process xt omega, and I'm interested in an integral of this type, a to b ft xt omega dt, then obviously the result is also a stochastic process. So what is the expectation of that random variable? So I want to understand the expectation of this integral, and that expectation and integration are interchangeable. This is something that we have discussed before, given that x has certain nice properties. So the expectation of this integral will be same as the integral of the expectation, which will be ft mu xt. Similarly, if I am also interested in the covariance, because of course I want to understand the first two moments, so I need the expectation and the covariance calculations. So the covariance calculations between integral ftxt and integral gtxt over the same domain a to b, that will be given by this kind of a formula. Integral a to b fs, integral a to b gt. This is our covariance between xs and xt, dt ds. So this is actually quite straightforward. So I'm not really going to show you the steps, but I think you can just do it very quickly in 1 or 2 steps yourself, or look up Whale-Portstone. Okay, so if I know expectation and covariance, I basically know the whole distribution, because I am working with Gaussian distributions. Why are they useful? So simple example. So if I take y as an integral of x process from a to b, then I can easily calculate the mean process of y from the mean process of x. So I will just use the first result here, where my f is identically 1, and I can calculate the mean process of the integral. Similarly, from the covariance process of the integrand, the x covariance process, I can again find the y covariance process. So if I take a simple integration over a time range, I know what is the distribution of the integral going to be. It's a straightforward calculation, so easily done. Also, suppose xt satisfies that class of properties A, capital A, that we have been using time and again. So one can show that if xt satisfies property A, then y will also satisfy property A. Because property A has the mean covariance continuity and the mean square property. If you look at the transformations here, you can easily see that if X satisfies those properties, then Y will also satisfy them, and I can prove that from the basic principles using the form of the mean covariance functions and the mean square convergences. Is that clear? Do you see why that should be so?
Yes, sir.
So it's just point by point checking that the A properties, there are quite a few of them, A properties, they all transmit through an integral. And obviously, if xt is Gaussian, the integrand is Gaussian, then the integral will also be Gaussian, because integral is after all a limit of summation process, and normal distribution is closed under linear combinations. So in general, if xt is Gaussian, then not only ft xt dt is Gaussian, but also if I define a two-dimensional process ys as hst xt dt, then that will also be Gaussian. What you need to crucially remember is that the f and h, they are non-stochastic. Otherwise, this will not be so easy. So the Gaussian property also transfers. And the fourth property is a slightly more mechanically calculation intensive property. And this would be very useful for covariance type of calculations. That is, expectation of this particular integral, a to b f prime bt minus ba and a to b g prime bt minus ba. If I take expectation of this product, so it's like expectation of x and y, that will be given by sigma square, which is basically the variance of the Brownian motion. So you can take it to be 1 if you standardize. But this is the contribution of f and g, and that contribution looks very simple. It's an integral a to b ft minus fb ft minus gb. So let me just show you a quick proof. So I'm switching to a different PDF file. So you see the new PDF file on screen, correct?
Yes, sir.
Yeah, and it is already
Yes, sir.
there in the Google Drive. So if you now check the Google Drive, there is a new file there. So whatever notes I am using through screen sharing, I have already placed them in the Google Drive. Originally I had 2 files, but over this weekend I created a third one, this one, because I saw that some parts were missing from the other 2 files. And word of caution, this is my handwriting, so almost surely you won't be able to read all of it. So if you are stuck, just ask me, I will read it out to you. So this is the property 4, that the one that I was discussing, f prime, etc. So how do I use it? So if you recall, I stated a covariance formula earlier, which I will show in this other file here. Let me just scroll back a little bit. Where is that? Yeah. So for a Wiener process, this is the property that we stated earlier, that expectation of Bs minus Ba times Bt minus Ba will be equal to sigma square minimum of T minus A S minus A. This is just the overlapping interval property, very easy to understand because of independence over disjoint intervals. So this is the property I am using to show this particular result. So if I use that, the left hand side I can write in this way. It's a little bit of manipulation, but if you just go through the steps, you will see that the left hand side, this expectation is essentially f prime integral g prime and then sigma square s minus a t minus a dt ds, which you can evaluate by integration by parts, and there is a little bit of change of order. So these are the steps which will give you the final result. So the crucial step is the use of that covariance formula. over overlapping intervals, and the rest of it is just high school calculus. So just look at these steps and ask me if you are not finding it clear. Otherwise, we will assume that this is clear to all of you. Just check the steps. You have done this kind of steps maybe thousands of times in your high school, but just go through them once. So is that okay?
Yes, sir.
Thank you. So this is again a more mechanical property, but as we will see quickly that these are very useful to find relevant probability distribution of relevant integrals. So as earlier we were looking at the property of a simple integral. So this was our leading example earlier. Where was I? I was somewhere here. That if I have an integral xs ds, then I can easily find the mean covariance function of that. So this particular property makes it even easier to evaluate. So if suppose I choose a equal to 0, b equal to 1, so I'm looking at a range from 0 to 1, and I take f and g to be identically same and equal to the function t, then this left hand side here becomes expectation of 0 to 1 bt dt whole square. So this is a very basic integral, and I want to know the probability distribution of this integral. So what do? I simply evaluate the right hand side integral. In this case, this will be sigma square 0 to 1 t minus 1 whole square dt. So basically I have sigma square by 3. And I already know that this integral has 0 mean. So the integral 0 to 1 bt dt will follow normal distribution with 0 mean and 1/3 sigma square variance.
Sir,
Yes.
sir, could you explain that property that the integral of a normal of a Gaussian process is also a Gaussian process? Could you repeat that argument?
So integration is summation, correct?
Right, but the summation is over infinitely many things. The normality does not go through over limit.
So when we do the finite linear combination, there is no question. Then we take the limit.
No.
And sorry.
No, when it is finite, there is no problem.
There is no problem. Then when we take limit, we use the mean square convergence property.
Oh, so what exactly is the theorem? That if it is mean square convergent, then normality goes through with limit.
Goes through with limit. This is not generally true, but for normal distribution, it would be true.
Okay, so we did not know this.
Just check this one. This is a little bit of a subtle point, but if I have the first two moments, normal distribution is fully characterized. So whatever error there might be, that error can be ignored.
Okay.
So do you remember how the central limit theorems work?
So your voice broke, could not hear you.
So again, I repeat, am I clear now?
Yes.
So do you remember how the central limit theorems work?
Yes.
What is it?
I mean, are you asking for a proof or the
basic idea of the proof? What exactly do we use? What is the fundamental trick that we use?
Yeah, we we characterize the, we use the characteristic function to do that, and then we use it up to the first two moments, and then bound the other moments as something of a-
Yes, and
Yeah.
same thing will work here
Okay. Okay.
because of the means.
Huh. What I wanted to
So,
emphasize.
so that would be like infinite product of Gaussian characteristic functions.
Right, right, but you can bound it, still bound it. Because you see, when you are taking infinitely many products, your components inside are also changing. Remember that binomial going to exponential type of formula? When you go from discrete compounding to continuous compounding? Can you see the
Yes,
connection?
sir.
I'm not sure whether you can see the connection. Because now that you are slicing it in finer and finer parts, each part, the probability distribution is also changing. Not the nature of the distribution, but the variance is changing. All right. Is that, does it make sense?
Yes. Yes.
So that's where you will need this argument.
I mean, what I wanted to emphasize is that this proof is not non-trivial.
No, absolutely not. Absolutely not.
Okay.
All I am trying to give you is the basic intuition that how your central limit theorem idea can be used again. But the finishing touches are certainly non-trivial.
Okay. Okay. Okay, sir.
But yeah, you are welcome to look up and ask me further questions. But a very nice reference for all these proofs are Karatzas and Shreve. Are you familiar with Karatzas and Shreve?
No, sir.
Okay. So let me just write it somewhere. I can write it in a chat here, correct? I can do that. Then you can see.
Post
So,
it on the classroom stream so that it can be referred to later.
on the screen. Okay. Okay. So what I should be doing is maybe open this file and write it. I do have a board, but I think writing here would be easier.
No, I think he is asking to write it on the classroom.
On the classroom. Oh, okay. Okay. Okay.
So that we can later see on what you have written.
Okay. So I will just share that line here, correct? You can see my screen here, right?
Yes, sir.
Okay. So I don't remember the exact title of the book. That doesn't matter because if you Google, you will get this book. So Karatzas and Shreve. It's a very, very nice introduction on the theoretical nuances of whatever models we are talking about. Okay, so can you all see this now? Navonil, Abhinandan, can you see this?
Yes, sir.
Yeah, okay.
Yes, sir.
So no, because then I will go back to my note screen and close this one, I suppose. So, okay. So the Gaussian property getting transmitted through integration is something that we are discussing here very intuitively, but there are some finishing touches and you can definitely ask the questions. The questions are all very relevant, but I will not spend time on that. I will just refer you to Karatzas and Shreve. Look it up And if there are doubts, then of course you are welcome to ask me and we can discuss. Okay, so let me come back to these properties. So these are the properties that I wanted to talk about, because they will be useful later on when you are trying to quickly evaluate mean and covariance of new processes. Okay, so that we have an integration theory, a somewhat complicated but still usable integration theory, and that integration theory we will be developing further towards our Black-Scholes model. And to get to the Black-Scholes model, we will need to understand what are the particular type of processes that we want to integrate, that we want to study. So we'll get there. In the interim stage, I also want to talk a little bit about the process of differentiation. If I have an integration theory and I am talking about a stochastic differential equation at the back, that was my canonical example, population growth model. So I will also need a differentiation theory. And you are all aware that differentiation is essentially defined indirectly through integrals. And that's exactly what we will do here, because directly defining a differentiation here would not be possible really, because we are looking at random variables. So we will take the back door. We will define differentiation indirectly through the process of integration. So what are the processes I'm going to differentiate? So let us take a process xt, which satisfies all the properties capital A. We say that xt is differentiable. So we use the same term, differentiable, if there exists another process yt, again satisfying capital A, such that the increment in x can be written as equal to an integral over y. So xt minus xa can be written as integral of a to t ys ds. So I'm defining differentiation through integration, because integration we understand now. So let us use that to define what is differentiation for us. So we understand differentiability through that I have an underlying process. If I integrate that, I will get back my original process. And then yt will be called the derivative of xt. And of course, keeping to usual calculus convention, we will denote it by x prime t. So this x prime t is basically this y. And symbolically, even though directly writing this is complicated, symbolically we will write ddt of xt equal to x prime t, except at points of discontinuity. And that, that check has to be there. So this ddt of xt being equal to x prime t is to be understood in the integral sense, that xt minus xa will be the integral of y, or integral over x prime. So is the definition clear? So I'm using the indirect definition, and because I know the properties in A are transmitted through integration, then they also need to be back transmitted. So I say that if x satisfies capital A, then I'll call it differentiable if y is also satisfying capital A along with this particular equality. So is the definition of differentiation clear?
Yes, sir.
So it is not a fundamental one, because I am using integration definition. So whatever caveats, whatever restrictions we put on the integration definition, all of them are also relevant to define the differentiation process. So this is our definition of differentiation. And then of course, we are also interested in finding the mean covariance from the original process. If I differentiate, what happens to the mean and covariance, and one can show that mu of x prime will be ddt of mu xt. This is, you have to think of this in reverse through the integration process, and the covariance of x prime s and x prime t, the autocovariance, that will be given by this del 2 del s del t of xs, covariance of xs and xt. So these are to be understood as in the reverse way through the integration definition, and then you can easily establish these things. But again, if you want to see the details, well, Portstone. And if you can define the first order derivative, there is no reason for you to stop. You can also similarly define higher order derivatives. So you can look at second derivatives or third derivatives. But that is just a matter of mechanical extension. So let us focus on the first derivative. If we understand the first derivative, the rest of the story will be straightforward. Okay. So now let us specialize to stationary processes. Stationary processes are very important for us, where the mean, covariance, etc. are independent of the time. Have you already learned the stationary process properties in time series?
Yes, sir.
Because this course runs in parallel, so I always use the analogy, because time series is essentially the data version of whatever we are discussing. So in time series also we have a stationary process. The same thing is true here in terms of a stochastic process. Okay, so if I have a stationary process, then I have these two properties which are quite useful sometimes, that the autocovariance of x prime is second derivative of the autocovariance of x with a minus sign. So I'm using this particular relationship that we have already stated, and then I'm using stationarity. If I use stationarity, then I can specialize and show that the autocovariance of x prime t is minus second derivative of autocovariance of x t. And second property is x and x prime are uncorrelated for all time points. So at each t, xt and x prime t are uncorrelated. Okay, so the first one, it's not difficult. So let me just show you the second one, how I show the uncorrelatedness. So I'm looking at the correlation between x s and x prime t. So this expression means it's a covariance between x at s and x prime at t. And I know that that will be given by del of del t rx t minus s, because it's stationary. We have already started out with stationary. And that will be given by the derivative of the covariance function of x at t minus s. So what I will do now, I will basically put s equal to t. So r of xx prime at t and t will be r prime x0. And because of symmetry, that will have to be 0. So this is just the symmetry argument for stationary autocovariance functions. So I must have this quantity to be 0, which means the left hand side also must be 0. So is the proof clear? It is fairly straightforward, but just a few mechanical steps. Is it clear? Can you just check and confirm?
Yes, sir.
It's just a matter of checking, and you are much better at this thing than I am. So I'm sure you will get it very quickly. So these are two important properties: how to find the autocovariance function of the derivative process, and also show that the derivative process and the original process are uncorrelated at all time points. This is statistically a very, very important property. Have you seen this before? Well, you have seen this before, but can you identify where?
Fisher information.
Yes. Yes, so you have given me the big answer. I was expecting a small answer. Yes, you are absolutely right. Very good. Very good. Fisher information is in the same vein as this. Any other application? There are smaller applications, more specific ones. Well, good for you actually. I didn't expect you to say Fisher information at the beginning. Any other specific applications that you have already seen? Have you ever discussed in class at least the linear model with stochastic regressors?
No, sir.
No. Okay. Okay, fine. You are now learning the ARMA model, correct, in time series?
Yes.
So if you look at the autoregression type process, it is actually a linear regression with stochastic regressor. Do you see that?
Yes.
Yes, sir.
And if I am going to justify the usual properties of linear regression there, I will need some uncorrelatedness property between the error and the past values of x, like that.
Yes.
Yeah. So that's another analogy with this one. That the change in a process is uncorrelated with the current state of the process. Regression is in discrete time, but if you think of it as infinitesimal change, then it is actually a differential equation. Does that connection make sense?
Yes, sir.
So maybe if you are familiar with stochastic regressors, it would have been more obvious, where we have y equal to x beta plus epsilon, where x columns, they are not non-stochastic. They have their own probability distribution. There also we need assumptions like this. And of course, in time series, the stationarity properties give you similar guarantees, so that you can actually use a regression type methodology to do statistics with time series. So, okay. So these are two properties for the derivative process, which we wanted to understand. And I will finish the derivative discussion with the mean square property. This mean square property will also be useful for other things. So what is the result? So let me first take the result. So we all know that the derivative in real calculus is like a limit of slope. So I look at xt plus h minus xt by h. So increment over a small time difference divided by the length of the time interval. So that's the rate of change. That's the slope if you think of geometry. Then I take limit, taking h to 0. And that limit, if it exists, then that's what I call my derivative. That's how we learn derivative, through a limiting process of the slope. For a stochastic process, we did not define the derivative through that path, because that path would have been more complicated. We defined the derivative through integration. But is this new definition consistent with our notion of the old definition? This is the answer to that question. That if I look at the slope for a given h, then I can show that as h goes to 0, this slope will converge to the derivative that we have defined in mean square sense. So this ms is mean square. So that slope will actually converge to the derivative that we have defined through integration in the mean square sense. And again, I'm not giving details of the proof, but the proof will use the definition of the integral, because the integral again is like a sum, and it will also use the Cauchy-Schwarz inequality. Remember that is this x prime is actually integral of some y, is defined through that integral process, that x is integral of x prime. So if I substitute that integral definition here in place of x, then this is an integral from t to t plus h over x prime. And then I look at the limiting property of that 1 by h integral. And for establishing that property, for establishing this convergence, at some point you will need the Cauchy-Schwarz inequality. So, okay. Do you see the strategy of the proof? I'm not giving you the whole proof, but the strategy is just write this difference here as an integral and then take the limit. And again, the limiting arguments will need a little bit of fine touches, but the essential part of the proof lies there. And that result, in essence, also tells me that if xt is differentiable and Gaussian, then the derivative process x prime will also be Gaussian.
Sir,
Yes,
sir, cannot we use a DCT type argument?
we will. We will use DCT type.
I mean, in the proof of mean square convergence.
Of course you can. But you see, you want to bound it by some squares. That will be easier to handle because we already have the assumptions on the squares. It is a DCT type argument, but you bound them by squares and then show that the squares will behave in the nice way.
Okay.
If you write it down, it would be, I think, very easy to see. You have got the right idea. You are going to use that kind of argument, but you do it on the squares. And because of Cauchy-Schwarz, you know that the squares will press the term you want to control down to 0. So I'm doing hand waving, which is very bad, but I think you can fill in the details. Can you see that?
Yes, sir.
Yeah, you have to write it out. So because I'm not doing any board work, probably that's the problem. But these kind of gaps, you should be able to fill in. Just give it a couple of minutes. And then that property actually implies that the derivative will also be Gaussian. Then that is much clearer because of this particular connection between the slope and the derivative process in the mean square sense. Because we have used this earlier, the derivative is also Gaussian is clearly established. So it's the same kind of argument that I think earlier Abhinandan asked me about how that limiting argument works. Correct? So it was the same kind of thing here, I think. Yeah. So in general, we tried to show that if x is Gaussian, then the integral of this type and even this type are also Gaussian. There was that limiting argument there, which we were discussing a little while ago. Same kind of argument will work here for the first part of the result, and that will also show the second part. Is that clear in general? Anybody has any doubts on this thing? Because this transmission of the Gaussian property is something which is very crucial for us. So later on, without any question, we'll just do integration or differentiation and still keep using normal distribution. And these are the theoretical justifications for that. So when we finally get to the formula, life would be very easy because we have all these very strong properties. So the final formula, manipulations on that, calculating probabilities on that will be purely mechanical because I know there is a normal distribution. But I need to know that, yeah, these properties that I am using so much, they are all justified. They have been proved somewhere before. Okay, so again, hoping that these things are clear, let me introduce you to the main formula of the continuous time part of this course. Remember that the main formula for the discrete part of this course was the binomial model. For the continuous time part of this course, our final target is the Black-Scholes option pricing formula, but the mathematical foundation of the Black-Scholes option pricing formula is the Ito formula. So now what we are going to discuss is basically the Ito formula. And how do we establish that? So we need to understand a little bit more about the Ito integral. So, okay, some sample of my terrible handwriting here. I will read it out slowly because I'm sure you are not able to read it. So we have already done one simple integration earlier, that integral of ds/ds, where we highlighted the difference from the Riemann integral and also the source of the difference. So that integral example actually was worked out from the basic definition, but of course, working out everything from the basic definition is never easy. We have to go through a lot of steps and a lot of manipulations and so on. So what we really need are some formula like integration by parts or the chain rule, the typical fundamental theorems of integral calculus. And I know that they will not be the same as the Riemann calculus because already for that basic example, the result was different from Riemann calculus. But we need a new formula. If I have that new formula, we can easily evaluate integrals. Like we know integral of sin x will be minus cos x, things like that. So the Ito formula, which is so well known, is essentially a kind of chain rule for the Ito integral. And that's what we are going to establish now. So we started out with this first example that integral bs dv was half bt square minus half t. I rewrite it in this way to highlight the following fact, that when I am looking at this kind of a result, half bt square, which is just a function of bt, the other side, I have actually two integrals. One integral is a dv type integral, and the other term is actually a dt integral. So I make the following statement that the image of the Ito integral, what is the fundamental building block? Bt. I can think of Bt as integral 0 to t of dbs. Notionally, this is just a representation. So Bt is an integral of dbs. So now what do? I use a function half x square. I apply this half x square function on the left hand side. So I get half bt square. So it's a transformation on the left hand side. What happens to the right hand side? What happens to the right hand side is slightly different from what would happen for a Riemann calculus situation, Riemann integration situation. Because when I use the same transformation on the right hand side, the transformed integral is not only an integral, not only a db integral. It is not of this form, integral 0 to t f db. We already have seen that. It is actually a combination of a db integral as in the here half dt square, and a ds integral which has given me half t. So the transformation of the right hand side under a nice function like half x square gave us two parts, not one single part, not one single integral. It gave us two different integrals. One is a dt integral which gave us half t, and the other is the bs dbs integral. Is this point clear? Is the actual question clear what we are trying to discuss?
Yes, sir.
So I want to understand how the Ito integral behaves under a transformation. A nice, smooth type of function. Nice function. Half x square is a very nice function. And through that elementary calculations, fundamental principle calculations, we know that this transformation generates two types of integrals together. So this intuition we now want to formalize as a general result. So what is our idea? Our idea is, let us introduce a class of stochastic integrals. These stochastic integrals are always a combination of a dt integral and a dv integral. Sum of a dv and a ds integral. So we introduce a class of stochastic integrals, and these stochastic integrals we call Ito processes. So that's our definition of an Ito process, as sum of dv and ds integrals. It need not be just one function here. I can have more than one, but there will always be two types. But these sums are stable under smooth transformations. So now if I apply a new function f on this, I will again get back a sum of a dv and a ds integral. So I started out with this notional identity, bt as integral dbs. So I can think of this as having a plus 0 dt integral notionally here. If I apply a smooth function here like half x square, my result will become half bt square equal to now a non-zero dt integral and a dv integral, ds dvs. We know this to be true for the particular function half x square. Is that true for a general class of nice functions? That's where our Ito process comes in. We say that a class of stochastic integrals are Ito processes. They will be called Ito processes if they are sum of dv and ds integrals, and the formulation that that structure is stable under a smooth transformation. So in place of this particular half x square, I can use any other function f with necessary smoothness properties. The new integral will again be a sum. So I'll just formally talk about the definition here and then stop. So the definition of an Ito process is the following. So we have already understood the basic intuition, but let me just make it formal. Take Bt as our Brownian motion on the triplet, omega, script f, and p. Ito process is a stochastic process xt on the same triplet of the form xt equal to x naught plus a ds integral, integral u ds, and a dv integral, integral v db, where of course v satisfies this particular condition. Now you understand what this condition will mean, that it is the square integral is finite with probability 1 for all time points. And you know why you need that. And of course, u must be ft adapted. This u function must be ft adapted, and v must satisfy this property. then these class of processes are called etho processes. A alternative shorthand description of the etho process is also given in the differential form. So xt is sometimes written in this shorthand version as dxt equal to udt plus vdv. You can see that this representation is just a restatement of this original integral statement. And from our early discussion, we already know that any notional representation of this type, this differential type, really means the integral. Because from the very beginning, we have given a sense to the stochastic differential equations through integrals. Integrals are the objects which really make sense. So this is the real definition, but can you hear me? Can you hear me, class?
Yes, sir.
স্যার
Yeah.
আপনার ভয়েস খুব ভেঙে যাচ্ছে।
হ্যাঁ ভেঙে যাচ্ছে আমি জানি আমি সেজন্য I don't know why. So is it okay now? So can we, because I'm going to finish in 2 minutes.
Now it is
Sir,
fine.
Yeah, so just bear with me. So the definition of the etho process is through the integral actually here, as in this equation, xt equal to x naught plus uds integral plus vdv integral with restrictions on v and u, but we sometimes write it in this shorthand as dx equal to udt plus vdv. In our earlier example, the original simple example, I can write it in this form that d of half bt square is half dt plus bt dbt, because that's what the integral was. This is what we have. Half bt square is half ds ds dt. So this is where I will stop, and next day, of course, we will talk about the actual formula, which I am showing here, but we will start the discussion from this point that we have defined the etho process, a particular class of integral process, sum of integrals, and we want to show that that formulation is stable under smooth transformations. So if I put a function g on both sides, I will again get the same form. So any questions or clarifications at this point? Because I am stopping here today, we will continue on Monday. But again, 2 things. One is check all the gaps that I have left here from Whale-Portstone or Oxendall, or for the more theoretical points, Karatzas and Shreve. But you do need to do that. That's one thing. The second thing is, at least before we start the ethos formula, I want all of you to review this classes so far and tell me if there are any problems that you are facing in understanding the basic theory. Because we are almost done with the basic theory, then henceforth we will basically do the applications. We'll use all these properties. So are these properties and their justifications clear? Because I have often not gone into formal proofs, but just given you some intuitive justifications. So that is something that I want you to check. Okay. So any questions now? All right, so we will resume on Monday then.